Okay, so high-resolution AI art, it's got a speed problem, a huge one. But what if I told you that a super fascinating new paper might have cracked the code by, get this, reaching all the way back into the 19th century? Today, we're going to break down Hilbert's a seriously clever method that uses a vintage mathematical curve to unlock the future of AI image generation. Let's dive right in. Oh, you know the feeling, right? You've tried to generate a massive print-quality AI image. You hit generate, and then you wait, and you wait some more. Well, that delay, it's not just your computer chugging along, it's a really deep, fundamental bottleneck in how these models actually think. And we're about to pull back the curtain and see exactly why.
All right, so here's our game plan for today. We're going to start with the big problem, the high-resolution bottleneck. Then, we'll look at this weird conflict in how AIs process images. After that, we'll introduce our unlikely hero, the Hilbert curve, and see exactly how the Hilbert AI system works. Of course, we'll check out the test results. Did it work? And finally, we'll talk about what this all means for the future of AI generation. So let's get right into it. What exactly is this bottleneck? Well, like I said, it's not just your hardware. It's a problem that's baked right into the AI's core logic. It all comes down to a process called self-attention. You can think of it as, well, it's how every single tiny part of the image talks to every other tiny part of the image to make sure the whole thing actually makes sense, you know?
And this, right here, is the absolute heart of the problem. Imagine the AI breaks the image down into a bunch of tiny pieces. Let's call them tokens. Now, for the AI to draw a coherent picture of, say, a cat, the token for the left ear has to know where the right ear is, where the tail is. You get the idea. But here's the catch. As the image gets bigger, the number of these conversations just explodes. And I don't mean it just grows a little bit. It grows quadratically. So if you double the number of tokens, you literally quadruple the amount of work the computer has to do. It's a computational nightmare, and that is what grinds high-resolution generation to a screeching halt. So this massive slowdown creates a really fundamental dilemma. It's kind of like a fight between two different ways of thinking. The way an AI needs to see an image to understand it is in direct conflict with how the GPU, the hardware that's doing all the heavy lifting, needs to read that same data. Okay, so check out this trade-off. I want you to think of your GPU as a librarian who's trying to shelve new books. The GPU-friendly way, that's like shelving books in the exact order they come in the door. It's super, super fast to put them away, right? But if you want to find books on the same topic, good luck. It's a total nightmare. Now, the image-friendly way is like organizing the library by subject. It makes perfect sense, but actually shelving each new book is slow and really inefficient. And for the longest time, you had to pick one. You either got a layout that was smart for the image or one that was fast for the hardware. You just couldn't have both. But what if you could have both? This is where our hero, and I'm not kidding, our hero enters the story. And it's a beautiful, really elegant mathematical idea from way back in the 1890s. It's called the Hilbert curve. So what on earth is a Hilbert curve? Well, it's a type of fractal, basically a continuous line that perfectly fills a 2D space without ever crossing itself. But its real superpower is this. As it snakes its way through the entire image, it has this amazing ability to keep neighboring pixels right next to each other. So even when you flatten that whole 2D image into one long single line of data, the parts that were neighbors in the picture are still neighbors in the line. It's this magical property called preserving 2D locality. And just like that, it completely solves our librarian's dilemma. The Hilbert curve flattens the image into one long line that the GPU can just zip through at lightning speed. But, and this is the absolute genius of it, that line is ordered in such a special way that it keeps the image's original structure totally intact. It is literally the best of both worlds. It's fast for the hardware and smart for the image. Okay, so we've met our hero, the Hilbert curve. Now let's see how the researchers actually put it to work. They built this whole system around it called Hilbert AI, and it all boils down to a really clever three-step process. And the whole process is just beautifully logical. So first up, step one is reorder. They take all those little image tokens and just line them up, one after the other, following the path of the Hilbert curve. Simple enough. Then step two is tiling. They take that super long line of tokens and chop it up into smaller, much more manageable chunks. Now this is really the key, because the AI now only has to pay full attention to the tokens inside its own tile, which just drastically cuts down on the work. But you might be thinking, that creates a new problem, right? How do all the different tiles talk to each other? Well, that's step three, sliding.
With each new layer of processing, the AI's little window of attention actually slides over a bit, which lets information pass from one tile to the next, kind of like passing a baton in a relay race. And to make absolutely sure the final image is perfectly coherent, they threw in two more clever tricks. That sliding window we just talked about, it means that as the attention shifts, the tokens right at the edge of a tile act like little messengers, carrying their info into the next tile over. And then there's this shared central region. It's basically a small, fixed area in the middle of the image that every single tile can see. It acts like a global anchor point, making sure the entire picture stays consistent and doesn't fall apart. All right, so the theory sounds amazing, right? But the million-dollar question is, does it actually work? Does it speed things up? Let's take a look at the results because this is where it gets really, really exciting. Okay, let's start with a pretty standard high-res image, 1024 by 1024. Compared to the old way of doing things, Hilbert had made that core attention process, boom, 2.3 times faster. That is a massive leap in performance right out of the gate. But hold on, it gets even better. When they cranked up the resolution to 2048 by 2048, where that slowdown problem is way, way worse, the speedup didn't just double. No, it jumped to over 4.17 times faster. What this shows is that the bigger the challenge, the better HilbertA actually performs. It just shines. This table really puts it all into perspective. The old baseline method takes a whopping 18 milliseconds for this one crucial step. HilbertA, it slashes that time down to just over 4 milliseconds. So how does it do that? Well, it makes the whole attention process 94% sparse. And that's just a fancy way of saying it's smart enough to ignore 94% of the pixel-to-pixel conversations that don't really matter. It just focuses on the important stuff. And this quote from the paper, this is really the key takeaway. This is the secret sauce. See, it's not just about doing less work by being sparse. Other methods have tried that. The real genius of HilbertA is that it does the work smarter. By using that Hilbert curve to create a layout the hardware loves, it makes sure that the work it does have to do is done incredibly efficiently. It just minimizes the time the GPU wastes fetching data. Now, let's be real. It's not a perfect silver bullet. The researchers are really upfront about this. Sometimes the method can create these faint visual artifacts, almost like little seams right along the edges of those tiles we talked about. It's a pretty minor issue, and it's caused by that fixed grid. But hey, it's an important trade-off to know about. So what's the big picture here? What does this all mean for the future? Well, this is way more than just a neat trick to shave a few seconds off your image generations. This innovation really unlocks entirely new doors for creative AI. I mean, for starters, this makes generating at ultra-high resolutions, we're talking 4K, 8K, maybe even beyond, a practical reality for the first time. It could also pave the way for truly fluid, real-time AI image editing. But maybe the most exciting idea of all is for video. The researchers think this same logic could be extended to a 3D Hilbert curve, one that moves through space and time. And that could be the key that finally unlocks efficient, high-resolution AI video generation. And that really leaves us with a final, kind of mind-bending thought. This research is just amazing proof that sometimes the answer to a super modern 21st century problem can be found hiding in a 130-year-old piece of mathematics. So if we can now generate these gigantic, high-quality images in a matter of seconds, how far away are we really from generating entire high-definition movies in just a few minutes? Based on a breakthrough like this, it might be a lot closer than any of us think.